then router 3, then router 4. Okay, this is our traffic engineering tunnel, and we are using it. After some second or after some minutes, some days, some weeks, okay, we will have one new pass, and this pass has better specification from the, for example, oldest pass. As you can see here, we have, for example, one router. This is the best pass, okay? When you are using the re-optimization, or for example, with the periodic re-optimization, okay, R1 should choose this pass, okay? In traffic engineering, we have a rule. First, the R1 should establish or reserve a pass from the a new pass, okay, from the R5. After that, it can break the oldest pass, because we don't want to interrupting the traffic that now are passing from the R1 to R4 from the old pass. Let me to show you. This means that first we need to signal the new pass from the R5. For example, we need to send RSVP pass message to R5. After that, R5 to R4. R4 should give us RSVP reserve message, and then R5 should give us RSVP reserve message. After establishing the new pass from the router 5, we can tear down the previous tunnel. Look at here, R1 tunnel 0 first should be signaled from the router 5, okay? After this signaling, and after the signaling is successful, we can break the tunnel 0 from the R1 to R4. This means we are making the tunnel before breaking the old tunnel. Why we need this, for example, criteria, this behavior? The reason of that is we don't want to interrupt the traffic. Now the traffic passing from the, for example, old tunnel, after establishing the new tunnel, we can forward the traffic to this new pass, and after that easily we can break the, for example, old tunnel. This is the make before break concept, okay? And this is so for example, useful for for not interrupting the traffic. This is a rule that we are using it by default in the for example, traffic engineering tunnel. Now we can talk about the shared explicit or SE style. Okay, look at this picture. This is our scenario for shared explicit SE RSVP style, and we are using make before break logic. Look at here, from this router, for example, R1 to this router R2, we have two paths. The first pass is going from the bottom pass, and you know that here we have, for example, 1, 2, 3, 4, 5, 6, 7 hops, and this tunnel established before, okay? After that, after, for example, some time, now we have a new pass from the top pass. And the new pass is the better pass and more optimal pass. You know that after re-optimization, periodic re-optimization, or manual re-optimization, or event triggered re-optimization, the tunnel head should change the new, for example, should change the pass of the tunnel from the new pass. You know it, okay? Now we know about the make before break. Let me to review it. For example, make before break means that when an LSR needs to reroute a TLSP, the new TLSP is built before the old TLSP is torn down, okay, for a specific T tunnel. The traffic is only switched onto the new LSP when it is completely set up to avoid or reduce traffic loss. Okay, now we have one, for example, a special scenario. In this scenario, as you can see, new pass or new LSP is passing from in some, for example, link from the old LSP. Maybe you say, what is the problem? Yes, let me talk about that. Look at here. Here on this link, we reserve some amount of bandwidth. Okay, for example, 1 megabit per second. And this link only has 1 megabit per second of capacity. We reserve the 1 megabit per second for the old pass. Now for the new pass, because we are using the make before break, we don't have the 1 megabit per second of bandwidth. Why? Because we reserved it for the old pass. Let me to review it again. Look at here. We have here 1 megabit per second of bandwidth, but this 1 megabit per second of bandwidth is reserved for the old TLSP. Okay, and because we are using the make before break, we can't turn down for example, old LSP. Because of that, first we need to establish the new LSP. But here we don't have for example, requirement of bandwidth, and because of that we can't establish the new LSP, and finally we have problem. Here we can use the shared explicit or SE RSVP style. This is the default behavior. You don't need to configure anything. Let me talk about that. The shared explicit or SV RSVP style that is used for TE ensures that make before break, okay, is issued. Let me to talk more about this. The bandwidth reserved on the link, for example, on this link, okay, that might be used by both the old and the new TLSP for a particular T tunnel is not accounted for twice. So interesting. Once for the old LSP and once for the new LSP. The same can happen when the administrator increases the required bandwidth for an existing T tunnel. For example, we have a tunnel, and administrator needs to increase the amount of bandwidth. We don't need to count double or twice the bandwidth, okay? The old and new bandwidth requirement are not reserved at the same time on the shared link. Rather, the highest amount of bandwidth is accounted. It's so interesting, okay? Let me to give you more information about this. Look at here. Here, as you can see, we have R1, for example, connected to this router. This is R2, okay? And also we have only 1 megabit per second in this link. And the old LSP now is using this 1 megabit, okay, bandwidth. And we need to use this link for a reservation of the new LSP, okay? Because the new LSP is better LSP, there's better pass, okay? And now we don't have more bandwidth, okay? Here our problem, this is why our problem. When we are using this, for example, condition, and the new LSP is passing from the old LSP, okay? And because the shared explicit is, for example, running in the traffic engineering, only for one time the bandwidth of link is counted. This means that when the new LSP request receiving to the R2, okay, R2 understand that this new LSP, okay, exactly is the same LSP that it counted the bandwidth for that LSP. Because of that, it can reserve again 1 megabit per second of bandwidth, okay? And because of that, when the new LSP is signaling, the R2 or other routers don't have any problem. Because of that, after the new LSP establishment, they can tear down the old LSP, and actually 1 megabit per second of bandwidth is remaining, okay? This is the shared explicit SE style. The old and new bandwidth requirement means the old requirement of the old LSP requirement of bandwidth and also the new LSP requirement of bandwidth are not reserved at the same time. You know it on shared links. This is a shared link, okay? And rather, the highest amount of bandwidth is accounted. Assume that the old LSP has the requirement of 1 megabit per second. In most cases, the new LSP also has a requirement of 1 megabit per second of bandwidth. But in rarely cases, maybe you configure the new LSP with more than the old LSP requirement of bandwidth. Only the highest amount of bandwidth, okay, is counted. For example, the old LSP has 1 megabit per second of bandwidth requirement, and the new LSP has 2 megabit requirement. Only 2 megabits should be counted for this link, okay? This means that we don't need to double booking of the bandwidth. It's so interesting, okay? Let me to review this feature about the shared explicit style. The shared explicit style or SERSVP style that is used for T ensures that make before break is issued. SE style is advertised in the pass message, you saw it, okay? This means that when an LSR needs to reroute a TLSP, the new TLSP is built before the old TLSP is torn down.